Swayam Prabha. Digital India. Educated India.
We will continue with our discussion on reference temperature method in this lecture, and then we will move on to some more topics which are of interest to us. Brief discussion on boundary layer transition, followed by some recapitulation of the governing equations of compressible flow from the viscous perspective. In the previous lecture, we had an introductory discussion about reference temperature method. Though we did not look at the equations per se, we just briefly talked about the concept, where we said that it is a very important approximate engineering method for predicting skin friction and heat transfer, and it extends to both laminar and turbulent hypersonic flows. It can be applied for supersonic flows too, and we essentially make use of results from incompressible flow theory and extend them with some compressibility corrections brought in through a reference temperature or a reference enthalpy. And this reference temperature or enthalpy is indicative of the temperature or enthalpy existing somewhere inside the boundary layer, which basically means that it is going to occupy a value intermediate between what you have in the free stream and what you have at the wall, and it gives surprisingly accurate results based on its ability to correct the compressibility effects. We are showing an instance where the reference temperature method solution has been superposed on the exact compressible laminar boundary layer solution. The red dashed line is the one which talks about the reference temperature method. You see a very slight under prediction, but remember that the black bold lines are basically talking about exact solution of the boundary layer equations. You have to solve these ODEs based on the respective temperature boundary conditions through a shooting technique, and it is a time consuming exercise. Every time you change the ratio, you will have to do a fresh calculation and so on, while the reference temperature method can be solved with much less computing effort, and that is where its importance as an engineering tool is undoubted. However, remember, it is based on certain simplifications. We essentially invoke the incompressible flow results, and we try to assume that the boundary layer remains a kind of a non-reacting layer, and if you want to bring in those realities further into the calculations, then perhaps you have to extend the models and bring in those realities, which could be your research problem too. Recapitulating some flat plate skin friction and heat transfer calculations that we attempted much earlier in lecture 21 of the course. It was the beginning of week 5 lectures, where we discussed about introduction to high temperature gas dynamics. So, you can look back at the lecture content, and then you may recall that we talked about a problem where flat plate at 0 angle of attack is immersed in an uniform airflow, and the chord length of the plate was taken as 1 meter, span was taken as 10 meters, and then there were two cases we did, the case A and case B. The case A was at sea level conditions, while case B was at 15 kilometers altitude or so. So, here we are going to proceed with the case A only. However, you can look at the case B later on when you find time, and try to apply what you learn over here in the reference temperature method discussion, and you will find that I am sure that even in case B you will find fantastic match between the reference temperature predictions and predictions from the the boundary layer theory results. So, we took the free stream pressure, temperature, viscosity based on the altitude, and we went out with the adiabatic boundary condition for temperature. We found out the free stream density from equation of state, the sonic speed from T infinity, taking R value as 287. M infinity was taken as 8. Based on the A infinity that we calculated, we got the V infinity, and then we read the tables from which we found that CF root REX for Mach number 8 is found to be 0.45, and thereby we came up with this relation for wall shear stress. Further, we found out the value of Q infinity, the free stream dynamic pressure. Now, we did the calculations at quarter chord, where x is 0.25 meters. So, calculation of shear stress at quarter chord location of the plate, we got the value of 298 Newton per meter square, and we are circling this value or indicating it with importance, because you will find this value coming back for comparison once we are done with the reference temperature method calculations. We would like to see how these values compare. Similarly, at x equal to 0.5 meter, that is at semi chord, we found a shear stress value of 211 Newton per meter square. Also remember, based on the basics of boundary layer theory, that closer to the leading edge, the shear stress is always larger. The shear stress spikes close to the leading edge, and then it decays rapidly as you move towards the later part of the plate, because of the rise in the boundary layer thickness, because it is dependent on the gradient of velocity. And then comes the temperature profiles for adiabatic and isothermal walls. We are talking about adiabatic wall, and we are at Mach 8. So, we are following a distribution somewhat like this, and as you can understand that the reference temperature technique will talk about a temperature intermediate between what you are talking at the wall and what you are talking about in the free stream. Further, we remember that for the case A, the T naught is found to be of the order of 3974 Kelvin, and the T adiabatic was found to be 3403 Kelvin. That was based on the recovery factor calculations that we have done over here, and the correlation that was used was under root of Prandtl number. These we had done in lecture 21, and now we are going to compare those values after application of the reference temperature method. In the reference temperature method, we bring about a definition of a reference temperature, which we indicate by T star as a function of all these parameters, T e, which is essentially T infinity, M e or M infinity, similarly again T infinity here, and this is of course wall temperature. So, it is a simple looking relation for T star, that is the reference temperature we are talking about, and then we fit in all these values which are applicable for our case, and then we find that T star by T infinity comes out to be this ratio, and once you plug in the T infinity value, you get a value of 2685 Kelvin, and this T star is what is going to be used further in our calculations, we will see soon. The reference density is calculated, of course, using the equation of state. Remember that T star is a representative temperature somewhere within the boundary layer, though we do not commit exactly where it is. Neither is it important for us to commit. Wherever it may be, the important point is that the pressure within the boundary layer remains constant, and it is going to be equal to free stream pressure only, and therefore, we plug in the P value as P infinity, the T value as T star, R is of course the specific gas constant, based on which you get a representative density. The coefficient of viscosity is obtained from Sutherland's law, where we fit in the reference values of mu, T and the parameter S, with which we are able to calculate the value of mu star by mu ref, and that is found to be 4.05. Once you multiply that ratio with the reference value of viscosity coefficient, you get the mu star. So, this is like viscosity coefficient based on the T star that you are feeding into the calculations. So, what we realize is that once we have calculated the T star based on the expression that we left behind in the previous slide, from this expression whatever T star works out, you basically adjust density, viscosity and maybe more terms which are yet to come based on this T star that you have defined as the reference temperature. So, everything gets kind of scaled with respect to the reference temperature. Applying the reference temperature method for calculation at the quarter card location, we have this definition of all these parameters, the REX star, the CF star, the tau W, etc. Remember that all these values are actually going to be kind of adjusted with respect to the T star that we have estimated already, and then based on that we calculate the RE value, for example, at the quarter card location to begin with. So, the RE value at quarter card with the star associated with it, because you are plugging in the rho and mu values which are based on the reference temperature. Remember that the velocity or the length scale are not going to have any kind of dependence on that, because they are fundamentally independent of that. And based on those numbers that you plug in, you get a value of Reynolds number at the quarter card. Similarly, based on the CF expression that we find over here, keeping in mind that this is basically the expression for incompressible flow. We calculate the CF here based on the RE at quarter card for the star condition, and then comes the tau W at quarter card based on the CF star and the rho star that you have estimated, and you get a value of 290.3 Newton per meter square, while from the compressible boundary layer calculations we have shown earlier, it was coming out to be 298 Newton per meter square. So, as an engineering tool, this is a fairly good prediction which we notice, and remember that there is a slight under prediction which we saw earlier even in the graph, where we had used a dashed red colored line to show that the reference temperature method slightly under predicts. We repeat the calculation for the semi-chord location, and then the Reynolds number at semi-chord location comes out to be this, and correspondingly you also see the influence on the CF this time. Remember, because it is the quarter chord location, so you will have a factor 2 here instead of a 4 in the denominator. Correspondingly, there is a increase in the Reynolds number, and that feeds in over here in the denominator, and the CF star changes. That has an influence on the tau W. So, at C by 2 it comes out to be 205 Newton per meter square. And then how does it compare with your compressible boundary layer calculations? It is again not too far. So, we have a very encouraging comparison that we saw over here. I would inspire you to look at the case B that we had discussed in the 5th week of lecture, where the conditions for case B, you can pick it up from there. You can pick up the tau W at C by 4 as well as tau W at C by 2 for that problem, and then bring out the tau W corresponding to those length scales through your reference temperature method, which has been discussed over here. That will be a really interesting thing to do for you. So, we talked about invoking the incompressible laminar boundary layer results and then tuning them to bring in the compressibility corrections through the reference temperature method. Similar things can be done for turbulent boundary layer, and then if you talk about the incompressible model in this form for turbulent boundary layer, again they essentially have to be modified this way, where the star values coming in over here indicates that you must have defined a reference temperature based on which the change has been made. And further, the turbulent flat plate heat transfer can be estimated from a Reynolds analogy relation, which works like this, where S is the Reynolds analogy factor, and you can get values of those factors from the following reference of Van Vriest. Van Vriest is a very big name in the area of compressible aerodynamics, and therefore you need to look at his publications, one of which is mentioned over here, and that will be helpful for working out the turbulent flat plate heat transfer. In a similar way, you can also do predictions of the CH for the laminar case, which I haven't explicitly discussed over here, but if you plug in the Reynolds analogy for the laminar case, you can similarly do a prediction for that based on the skin friction calculations that we have discussed already. One of the most latest methods based on reference temperature is the reference enthalpy method, proposed in the following reference of Maeder, and you can also have a look at this paper if you manage to find it or find time to access and go through it. So, these are some of further inputs which you can explore in your spare time. As we are discussing about turbulent boundary layer, it is important for us also to understand how the laminar flow transitions into turbulence, and then it is worthwhile to look at a plot like this, where we see that if we rethink about the hypersonic entry of vehicles back into Earth's atmosphere, we were talking about altitudes of the order of about 100 kilometers or so, and velocities in terms of kilometers per second spanning up to 10-12 kilometers per second. And if we follow a typical flight path of a lifting entry, we were talking about values of this kind. And then if we make some assumptions that the vehicle that we are considering is about a 10-meter long vehicle, and laminar turbulent transition occurs at about Reynolds number of 1 million or so, then this vehicle will actually see mixed regimes of laminar and turbulent flow. At these kind of altitudes, it may go through purely laminar flow, while at these altitudes, at lower altitudes, it is likely to see a lot more turbulent flow developing on it. And then transition from laminar to turbulent flow makes a lot of difference in the sense that the skin friction coefficient, the heat transfer coefficients are dramatically increased if the flow becomes turbulent, and therefore predicting the point at which the transition onsets or the region over which it onsets is always a big question. And in this context, though we have through an engineering tool tried to address the problem by introducing the reference temperature or enthalpy method, but that does not of course indicate that on which regions of the body should we think laminar, on which regions we should think turbulent, and so on. And typically a compressible boundary layer will show up in this form, where portions of it is laminar close to the leading edge, and then you have a transition point which is always very difficult to predict, and then beyond it you have the turbulent boundary layer forming, and the changeover of course happens over a certain region which we call as the transition region. If we call the transition point as at a location of x t, then the corresponding transition Reynolds number would have to be defined in this manner, where x t is the length scale you use, and for the fluid properties you use the free stream properties existing at the edge of the boundary layer. For accurate prediction of skin friction and aerodynamic heating to the body, knowledge of the transition Reynolds number is of course extremely critical, and unfortunately though we do not have any theory which can predict the transition Reynolds number very accurately, and any knowledge concerning its value for a given problem must be obtained from experimental data or very high accuracy in numerical simulations, and therefore it remains a very complicated problem. But again, we need to have some appreciation about this, because without understanding the fact that the flow on any kind of vehicle that we are talking about in this regime would see mixed laminar as well as turbulent flows existing, and transition lies in the boundary. The better we can understand transition, better are our chances of predicting the skin friction or the thermal load on the vehicle more accurately. Some of the important points with regard to boundary layer transition are briefly mentioned. Various parameters influence the transition Reynolds number. A few major points are mentioned below. The Mach number that is existing at the edge of the boundary layer, it always has a strong influence on the stability of the laminar boundary layer, and through this on the RET. T stands for transition. Boundary layer stability theory shows that stability of laminar boundary layer is generally enhanced by an increasing Mach number. So, higher the Mach number, higher is its stability, and therefore the onset of turbulence will be happening at a higher RET value. So, that is the basic idea behind this point. Since the skin friction and aerodynamic heating are considerably smaller for laminar in comparison to turbulent flows, the relatively large region of laminar flow that can occur over a body at hypersonic speeds is a very advantageous design feature. Therefore, the attempt is always towards retaining extended laminar regions if possible on the vehicle surface. Transition is much sensitive to disturbances that can come from its immediate environment. It could be free stream turbulence, it could be acoustic disturbances, it could be surface roughness, which includes some protrusions which are lying on the surface, which act as trips for the boundary layer, and disturbances that are introduced into wind tunnel flows from active turbulent boundary layers on the walls of the tunnel. So, that is important for model testing in the wind tunnel flows. The phenomena can significantly affect transition behavior of a hypersonic boundary layer. That means, transition onset will be expedited if you disturb the flow significantly. That reduces the RET value for a given problem. The unit Reynolds number is defined as the Reynolds number based on unit length. For example, x is taken as 1 meter, yielding the unit Reynolds number per meter respectively. That basically means that if you are talking about REx and you are talking about the length to be 1 meter, then this basically becomes unit Reynolds number, and it has been found from experimental data that there is a correlation of transition with unit Reynolds number. Therefore, depending on the unit Reynolds number that you maintain, especially in a wind tunnel test, you may be able to see transition happening at different Reynolds threshold Reynolds numbers. Three-dimensional flows can have a strong effect on boundary layer transition. Note that as angle of attack of the vehicle is increased, transition moves rearward on the windward side and forward on the leeward side. So, if you are exposing, let us say, a conical flow to such a cone to a flow which is approaching it at an angle of attack, then we are talking about increase of the angle of attack having an influence on the transition. The transition moves rearward on the windward side. So, if this is the windward side of the body, the transition point will move further rearward, and at the same time on the leeward surface of the body it will move towards the leading edge. So, that is the point we are trying to make here. The world temperature has a significant influence on transition. In the case of boundary layer cooling, the laminar boundary layer is more stable. That means, cooling of the wall leads to increased stability of the boundary layer, and therefore, transition is delayed. So, we say delay of transition in such a case, and transition may be expedited if you heat the surface of the body, because that can lead to destabilization of the boundary layer, and transition can occur earlier. So, these are of course studied in hydrodynamic stability analysis, and it is an involved area, but if some of you are interested, you can explore further into books which cover this area, which will give you a better idea about how to predict transition to a reasonable level of accuracy, either by using experimental methods or by high efficacy numerical tools. With this, we move towards the end of this lecture by saying that we would like to now start revisiting the governing equations of viscous compressible flow, since we were talking about either boundary layer kind of solutions which are applicable where we actually have a very thin layer of viscous flow developing on a body, or engineering correlations like the reference temperature method, which talks about extending incompressible flow results with compressibility corrections and trying to predict skin friction and heat transfer coefficients both in the laminar and turbulent regimes. But remember that all these kind of approaches are not really applicable to complicated vehicle geometries, where not all of the flow happening on such a complicated surface can be either categorized as a boundary layer flow, or we cannot even say that when the flow complicates because of its geometry, that these nice engineering correlations are also going to give us reliable results. Again, if we confine to only inviscid methods, then there are certain very important phenomena like separation of the boundary layer, shock wave boundary layer interaction, etc., which goes unaddressed, and therefore, finally, there is no way but to look at the complete viscous compressible flow equations. And not only that, since we are dealing with high temperature hypersonic flows quite often in the context of this course, we also have to recall about all the other equations which have to follow, including the chemical reactions that we have to include in the model, the concept of partial pressures. All these have to be included, and therefore, it is once again a good time before we wrap up the course to have a recapitulation of the governing equations, and we also would like to look at these equations to a slightly greater level of detail in the next 1 or 2 lectures, where we try to discuss it from the point of view of some of the open source flow solvers like the Hy2Form in the OpenForm platform. So, these are our compressible Navier-Stokes equations. We have been looking at them, we have studied them since long, right from the beginning of the course, but again, since these are complex equations, you have to return back and revise them from time to time, so that you remain very familiar with them and you are also able to write them with fluency, recall all the terms, the significance of all the terms. You should be able to write them in different forms. For example, the most compact form of the equations is always through the index notation. So, you should have fluency with the index notation. You should remember how you express the stress terms in a generalized form. You need to recall about the significance of all the respective terms, starting from continuity equation to momentum equation to energy equation. So, without going into too many details, I am just showing it in the form of slide, just trying to recall that you need to revise them from time to time, so that you recall the different forms. Since in the next 1 or 2 lectures we are going to spend some more time looking at these equations, again from the point of view of some more specifics in terms of models and so on, when they are implemented in actual flow solvers. And you must be also recalling the different forms of the equations, starting from their integral form to the differential form, the Eulerian framework, the Lagrangian framework. So, when we put them together, it actually looks like a framework. We see over here, we have been looking at this framework since a long time now, and I hope that this picture is very firmly set in your minds by now. Once again, please recapitulate them. We are going to elaborate them and add on some more specific inputs with regard to them from the context of viscous compressible flows, with reactions included and so on in the next few lectures. So, once again, before I finish this lecture, look at the different forms that you have over here: the infinitesimal fluid element form, the finite control volume form, the Eulerian, the Lagrangian, and the Gauss divergence theorem, which communicates between the two sets. The different forms of the equations, the integral forms that you see here, the differential forms that you see over here. In some of the forms, that is the Lagrangian forms, you see the use of the substantial derivative. And some of the terms may not always be figuring. For example, body force terms may not always figure in all kinds of flows. Viscous terms may not always figure. For example, if you are solving inviscid equations, then some of the terms will get simplified and so on. So, with that, let us conclude this lecture by saying that in this lecture we initially discussed about reference temperature method and solved some problems. We had a brief discussion on boundary layer transition, and we recapitulated the governing equations of viscous compressible flow very briefly, though, keeping in mind that we would like to elaborate them from an application perspective in the next few lectures. Thank you.